Hello everyone, thank you for joining this talk. This time we are going to talk about modern C++ templates, and we are going to talk how we can improve the way we are dealing with them so we can improve user experience, but also developers experience, because we are going to talk about some future proposals for the C++ language. My name is Mateusz Pusz. I'm the principal engineer at EPAM Systems and also the head of the C++ Competency Center at this company. I'm also a trainer and a consultant on my own. The plan for this talk is to, first of all, scope on the user experience. Then we are going to talk about new toys that we have in our toolbox in C++20. Next, we are going to scope on the proposals and possible future changes to the language. And at the end, as this is C++, C++ is about performance, we are going to cover this part as well. As we are quite tight on time, so I will answer the questions at the end, the most rated ones. If there will be questions regarding some slides, and there will be plenty of them, please refer to the slide number. It's in the bottom right corner here, and this will allow me to go back quickly and actually provide the content or context to which the question refers. Without further ado, let's start with the first chapter, so the user experience. I don't know if you are aware of, but I'm right now in the development of the physical units library for C++. The plan is to make it possibly a part of the next C++, probably not C++23 because of COVID, we didn't have enough time to make it a large release, but possibly C++26 if the committee agrees that we need such a library. If not, it will be just a library, or it will be library on GitHub, Conan, and other package managers, so you can always use it. But this talk is not about the library, but still I would like to provide you some context where I'm from and basically why I have some issues that I want to solve and how to address them. So first of all, what a physical units library do? Such library, first of all, does a really simple computations on quantities. You can get any quantity divided by 2 and you will have 5 kilometers. Right? We can use unit conversions. Hours to seconds, add kilometers, meters, get meters, and so on. But we know all of this from std.chrono, right? It's not anything new, so we are used to that. What's different is this part, that we can work not only on one dimension, but on many of them. Right? So we can divide length by time and get velocity. Right? We can multiply those and get length, and so on. You can also multiply two quantity of the same type, the same dimension, and you will get another dimension like area. Or you can divide 2 quantities and get just a scalar dimensionless value. Or you can actually divide a value by some quantity and you may get another quantity like frequency in this case. In the exercise, during the talk, I will refer to such a simple example. My task and my intent is to create a simple average speed function that takes length and time and return speed based on this on those arguments. For my common use cases, I try to provide support for kilometers, hours, miles, hours, and get the speed in proper units. I expect compile time safety. I expect support for multiple units and unit prefixes. I expect no runtime overhead. I expect that the binary produced by this, assembly produced by such code is as fast as working on just plain doubles. Let's see how this simple example can be implemented in different libraries. For example, boost units, probably the most important, the most common one, the most popular one in the industry. We provide quantity of length, quantity of time, we get velocity. This actually works on SI units, not on specific units I provided, but for this case it doesn't matter. We are talking right now about user experience, not the functionality. This is not talk about physical units. But notice that this is quite nice. This is quite nice for a developer, right? It's easy to understand, easy to type, hard to make errors. However, if you make an error as a user using such an interface, this is what will be printed by GCC 10.2. In function, and here goes the function name. Notice the 3 dots at the end because this is not the end. So this is the continuation of the log. Error could not convert boost units operator star with and another screen from and to and more screens to follow. So basically this is not a good user's experience for such a simple function, right? Dividing length by time is one of the simplest things you can do in a physical units library. There are things that are more complicated and involve more different dimensions and units. This is one of the simplest things you can do, and you get a really long, huge error, and it's not easy to understand what happens here. This is in GCC. Now, what about Clang? Clang is known to provide shorter and better diagnostics in error logs, and actually, this is what Clang provides. No viable conversion returned from value of type quantity to function return type quantity. And I expect right now everyone knows what's wrong with this function, right? Or not? Right? Short error messages sometimes are not necessarily better. They don't provide enough context. And actually, this is not the end of the error log, because Clang tries to be helpful and provides more hints, like candidate constructor not viable, and provides all of the candidates that can be useful here. So you can analyze this log and find out if it suits you, right? And more, and more, and even more. And the information that some candidates were ignored or disabled, or there are explicit constructors that are not candidates in this case. And at the end, I don't know why, but the compiler tries to confuse me, says there is no return statement in the context function, even though there is a return statement. Okay, but this is boost unit. Maybe let's try another library. Let's look into another really popular library created by Nick Holthaus. By the way, I don't want to say anything wrong about these libraries. Those libraries are created many years ago, started many years ago, and they are really great and provide and have wide user base, and they are successful on the market. It's just that right now with new modern technologies, we can probably do a bit better. This is how you can do in the other library. You provide length, time, and get velocity in meters per second. Again, nice user experience for developers, and for the users, it's a bit better because this is the full error log. We have static assert, units are not compatible, but still it's not that easy to understand what is the cause of this static assert to happen. In Clang, it is similar. Static assert failed due to requirement, units are not compatible, and there are some information about specialization instantiation of this is convertible unit trait. So a bit more context, but still not easy to read. So things to notice here is that static asserts are not often the best solution. First of all, static asserts are implementation details. They do not influence the overload resolution process and name lookup, right? So if you need this, static asserts are not for you. And also, for some compilers, as you've seen, there is not enough context to understand still what is the source of the error. Especially if you cannot see the sources of the function, assuming that you have only a header file. You don't know when the static assert was actually provided in the function, how was it called, and so on. So I would claim that in most template metaprogramming libraries, compile time errors are rare. It's hard to break string. It's hard to break vector for it to not compile, right? But there are some libraries like this one, where actually compile time errors will happen very often. This is actually the main cost to create such a library, just to generate those errors for the user, for the engineer working with physical units, to make sure everything is correct and consistent. And for such use cases, so for physical units libraries and similar, we have to rethink how we are doing template metaprogramming in C++. And this is how the title of this talk originated from. But compile time errors are not the only point of user experience. Sometimes we also want to debug stuff, right? So let's see how the debugging part works here. This is for boost units. I just want to write a breakpoint here in a correctly written function this time. And this is what I get in my IDE. For the arguments, D and T, I just get the type unit quantity boost unit unit double, and for type T I have boost unit quantity boost unit unit double, which suggests that this is the same type, but it's not, right? Which is not helpful at all. Actually, it's totally misleading. So if you want to go to the GDB and find out actually what the function is, this is what you get. And as this time this is a template function, you want to know exactly what you are dealing with. What is the unit here and so on. But I expect that from this function definitions, from this function instantiation here, you cannot easily reason about what happens here, what are the units. And you are lucky that actually dimensions are provided strictly in the text, because otherwise it will be also hard to understand what is the dimension here. The same case is for the other library. So for the whole house one, again, the IDE provides the information that D is just a unit of double of linear scale, and T is also a unit of double of linear scale, and we don't have any information what is the dimension here, what is the unit, and so on. Because the type is too long for the IDE to present in a nice way for the user. So the IDE chose to shrink the type here in order to fit in the graphical user interface box. And if you're going to the GDB to see the breakpoint, it's shorter, but still I think it's not that easy to understand what happens here, because you just have a lot of ratios on the list for first and for the second argument. This is not easy to understand that we are talking about length and time and what are the units here. So what I want to tell you is that type aliases are great for developers, but not for end users, right? We as developers cannot live without using aliases. It will be so hard to write code without template aliases, without template or just regular aliases, in order to maintain our code and develop it in a correct way, right? Writing all of those instantiations by hand, it's really hard sometimes. However, those aliases are lost quickly during the compilation process, right? Those are only the alias for the developer to improve the developer's experience. As the result, the end user seeing the compilation errors or debugging the session, seeing the types as C++ language sees those types, which are really huge template instantiations in those cases. This should be supported, this should be addressed by strong type devs. And for many years there was a quest, and actually this quest was by Walter Brown to provide those to the language. The first paper I found about this was in 2004, the next one in 2005, and the next one in 2013, another revision in 2013, but the last one I found is 2015. And after that, the official path of getting strong type devs to the language stopped. And also, for your reference, for your information, Walter is right now retired from the ICC+ committee work. So if someone wants to help me in pursuing this path in order to add strong type defs, we have to do it by ourselves. We have to start writing papers, start writing proposals, trying to standardize this, if it's possible at all, to find an agreement in the committee how this feature should work, because Walter tried really hard and he failed. Maybe you can find some compromise, but it's not that easy, and we have to try if you want to achieve this goal. In the meantime, there are some libraries that you can use for strong typing, but they don't cover all of the grounds, especially for types like quantity. They will not work correctly because they do not easily expose all of the interface, all of the operators and constructors and so on. So they are good to make strong types from double or integer, but not to cover, for example, make a strong type over vector or string. So what we can do instead, for now, as a workaround, we can use inheritance. Every time we have such long template instantiation, we can say this is a structure that just publicly derives from the template instantiation specialization. Similarly to strong type defs, those types do not vanish during the compilation process, so we should be fine with debugging experience and with compilation error logs, because those types will be present there. Also, base class can, if you have a function taking base class, can work with the derived class, right? So if there are any non-member functions of base class taking the base class as an argument, also the derived type will be able to be passed there. So you don't have to rewrite code. It works already with derived classes as they are in the language. However, alternatively to strong type defs, our speed, if there are any non-trivial constructors in the derived dimension, they will not be automatically exposed in dimension speed, right? You have to retype them or import them directly by hand to the structure. Also, all of the operators that can be provided there are not explicitly provided for this type. Also, if you have, for example, things like operator plus here, this operator plus will return just a derived dimension rather than dim speed as a derived class, as a return type of this function. So this is there is some compromise, and it seems to be a good fit for simple empty types. Things that do not provide much interface. For my case, these are dimensions, units, all of those are just tag types, so they are fine with inheritance, but for things like quantities that have interface like stud chrono duration, it's not possible to do this in this way. But this is fine. This already provides us a really nice interface. For example, this is how we can implement the same simple example in my library. We have SI length of meters, SI time of seconds, and we get speed in meter per second. If you make the same error, the same mistake here, this is what we get in error log, and this is all. In function, error could not convert from to. If you look here, this is exactly the same what developer sees, right? It's just additional namespaces are added as a prefix. So SI speed, SI meter per second, SI length, SI meter, SI time, SI second. So this is already quite good. Also notice what is the type produced by this invalid multiplication. This is also quite short one, saying this is an unknown dimension where exponent list contains dimension in exponent 1 and time in exponent 1. So this is not speed. Speed would have exponent -1 for time, right? But if it has 1, it's unknown dimension. It's something that was not defined in the library. And there is also information about unit, that is an unknown coherent unit of this dimension. So you can easily reason about, or easier reason about, what happens here, what is the source of the error. If you go to the debugger, you will get all of the information. We'll get information for length with the unit, and for time with unit. If you go to the debugger, you'll have information exactly as the user sees it in the code. So such a simple thing like providing a child class that is basically derived from the template instantiation makes a huge work for us already for the user experience. This is nothing new. This is something that was in the language forever. But we tend to prefer aliases rather than strong types, which I basically think are not as good in those use cases. They are great for developers, but not for users. And we should think about our users when developing our libraries. I would also like to show you another example, a simple one this time, and we'll go quickly through this one. We just want to divide meters, seconds, and get acceleration. This is of course another error, because you have to have seconds squared to have an acceleration. So we have another error saying conversion from non-scalar type requested, and we don't know much what is the problem here, but the error log is quite short. For the other library, it's pretty similar. We have information static assert that units are not compatible. For my library, the error log is also short, but notice one thing. There's information that conversion from speed with unit meter per second to non-scalar type acceleration in meter per second square is invalid. But I never provided information about speed here. I just provided this equation. Right? So what the library does in order to reason about that, this is user-provided derived type for speed rather than just multiplication of length and time, so the exponent 1 and -1 for time. Just to make it more clear on this slide, you have division of length, time, you want to get speed. This is an operator. And how to form a speed dimension having those two quantities of different dimensions. At the very beginning, I work with a type trait. I called it downcast traits. By default, it did nothing. It just provided the same type. And then for each and every dimension, I had to specialize it, saying that if you will ever see derived dimension of dimension length in exponent 1 and dimension time in exponent -1, then provide speed as an answer for this dimension. The same for area, and so on. However, the problem was that I had to provide those traits for every new definition of unit and dimension, which was cumbersome and error-prone. I didn't like it, so I think 2 years ago at CPPCon, together with Richard Smith, we were able to find a better solution. So this is what we have right now, right? We are deriving dimension, derived dimension, and we provide a strong type dimension speed for this specific template specialization or instantiation. The facility works as follows. I provide 2 additional helper types here. One is called downcast base, another is called downcast child. Downcast base just takes the type of the base dimension here, right? Through CRTP idiom, QC recurring template parameter idiom. And dimension speed also works with CRTP. It provides its own type as the first argument here, and the type from which we should derive this type. So this type derives from this one, right? This is the type to derive from provided as the second argument. With such an inheritance tree, I can provide the facility that works as I shown you before. How it works? First, we have downcast base. So this class. It takes base type, returns a downcast base type here, and also declares a function called downcast guide that takes this type, downcast base, as an argument. So it can be found with ADL. It's a friend function. We don't know what it returns for now, so we are returning auto, and we don't provide any definition in this case. We are just declaring this function, so it can be called with this type, because friend functions can only be, in this case, hidden friends can only be found, can be called if they take the argument of this type. Then I have a concept called downcastable that requires that my type t that I want to be able to be downcasted has actually this downcast base type inside, and that basically this type t is derived from this downcast base of this type. And then I have downcast child, so the one provided here, right? And this one takes the target, which should be provided as target of our downcasting, and downcastable type to be downcasted. We are inheriting from t, and right now we are providing the definition of the function declared here. It's still auto as a return type, but now we know what's the target, so we can return it here. We define it here, provide it here, and now spreading the information between two different classes, we can make the downcasting facility work. This implementation is needed, and it was so tricky that I wouldn't probably be able to reason about it and find it out by myself. Richard helped me with it. Because if we provide only this function here in downcast child, we would not be able to call it, because we are not in the correct structure here. So basically, this argument is of a different type than this one, and this is a friend function. So it will not be possible to call this function if it was not declared in this one. And I cannot define it here fully because I don't know what's the target type in this class. The target type is only known here. So the first declaration serves to be able to call this function. The second definition serves to provide the output from this function. And now we want to actually implement this downcast facility. So I'm implementing some downcast implementation helper here, and it checks if type t has downcast guide provided. I'm calling this downcast guide and reason about what's the type provided by this implementation. Otherwise, I just return the type, the same type, because I don't know what's the user provided type for it. And has downcast guide? It's simple. It's just a simple concept that requires that the downcast guide of t is defined. So it's being found through argument-dependent name lookup on type t. And this makes the trick. And I found already a few use cases in my library for those. Downcasting dimensions and units is one thing for that. So I can basically, through some arithmetics on types, I can end up with a new type and find out if the user provided a better name for this type rather than this long, huge template instantiation. If the user provided a better type, I'm switching to the type provided by the user. Otherwise, I just end up with this unknown dimension type saying that this is something that user didn't specify, that you've seen on the previous slides. Also, this is useful for other use cases. For example, my base unit definition only has information about the scale, the ratio to the other unit. But for example, doesn't provide any information about the symbol that should be printed in the console output. This is provided in a child class that knows all of the context. And thanks to downcasting, I am able to find this context and print everything as needed on the screen. Okay, I see a question from Peter. As it's exactly for the slide, I have it right now, so maybe I will try to answer this one. Does downcastable in type alias downcast guarantee the downcast implementation if context is true? Or would downcast implementation be called on other types as well? the downcastable context here, right? On the previous slide, I shown that it checks if there is a downcast base type inside and if actually it derives from the downcast base. So I think it's enough to make sure that this class was meant to be used with downcastable feature. But sometimes, for example, it may not be the type provided by the user may not be known or was never provided. So, for example, some base derived dimension type that is being constructed inside the engine with basically accumulation and arithmetics on exponents of different dimensions may end up with some specific sequence of exponents that was not provided by the user, but still this base dimension created by the engine is still derived from the downcast base, because it is meant to be downcasted. Otherwise, it will not work. I hope, Peter, that it answers your question. If not, we can talk about it offline, because I'm not sure if I correctly understood it. We can talk about this later on if it was not enough. Okay, let's move on. So this concludes my user experience chapter. These are the things that I put in order to make the errors and debugging experience on the next level, I think, comparing to the other libraries on the market. It's a great improvement, and this is why many users already switched to my library, even though it requires C++20 for the implementation, because I require concepts and other features that I'll be talking about later on. And now let's switch to the next chapter, to the new toys in a toolbox chapter. First, we are going to talk about non-type template parameters. If you are familiar with chrono duration and stud ratio, you know that stud ratio is a class template taking numerator and denominator. Two values, not types, two values. And then exposes those as members. However, they are not exposed directly, because you want to make sure that, for example, ratio of 1 and 2 is the same as ratio of 2 and 4, right? So that's why actually numerator and denominator is provided with some actual additional calculations involving, for example, greatest common divisor, to make sure that you are basically simplifying this ratio to the same form, no matter what numerator and denominator was provided. And all of those are another class templates. Static sign is a class template. Static ABS is a class template, also using static sign in the implementation. Static GCD is another class template that actually works in some kind of recursive way, and uses static ABS class templates again. As you can see, there are a lot of class templates instantiations needed in order to calculate such simple ratio, such simple type here, which makes it slow to compile. And it's not all, because, for example, if you want to multiply ratios, you have functions like ratio multiply, ratio add, ratio subtract, ratio equal to, or equals, I don't remember exactly what's the name. And all of them are, again, class templates. So if you want to implement those, you call static GCD again, and do some save multiply class template. All of this involves a lot of instantiations in a compiler, and each instantiation is a dynamic allocation in a compiler, so it takes time. You can simplify those. Actually, with C++14 or current state of the library, you could make it easier. Actually, you can use consexp. So we have stud GCD in the library already. We can just use it. It's consexp right now. We can implement ABS as consexp function, not a class template. And with this, we already make a huge improvement, and we are also able to better reuse our code. We don't have to have GCD as a function and GCD as a class template. 1 is enough. Also, this ratio multiply class template can be implemented in terms of those functions. Context functions are great and improve reuse of the code and performance here. However, in C++20, non-type template parameters were hugely extended. Right now, the definition says that non-type template parameter is either a structural type, placeholder auto, or basically CTAT, so class template argument deduction type, placeholder here. And what structural type means? Structural type is a scalar, a value reference, or literal class, where all base classes and non-static data members are also structural types. Having such a wide definition of non-type template parameters, we have to find out what it means for two values to be equivalent for template instantiation, right? If you specialize template with two values, you want to make sure if this is the same specialization or maybe different specialization. So you have to be able to compare those values somehow. And for this, we introduced a term called template argument equivalent. And template argument equivalent values are values of integral types, which was always the case for NTTPs, and numeration, which was always the case, null pointer, but here's something new. We can instantiate templates with floating points in C++20. This was always there, but again, we can instantiate with array types, with class types, with template argument equivalent subobjects, and union types even. So it opens the doors for many new use cases in the language. So let's come back to our ratio. Right now you can implement ratio as just a simple structure, even not a template. It has two members, numerator and denominator. It has a constructor that does all of this magic of simplification for numerator and denominator. Again, using the same context functions. Right? And now, instead of ratio multiply class template, I can write multiplication operator that again uses those context functions. And I can not only right now multiply ratio with ratio, I can multiply ratio with integer and integer with ratio. And it works. So having such things allows us to refactor the code that could be written as this one, so derived unit of some yard, symbol, length, and some ratio, and then ratio multiply 1/3 of a yard and so on, allows us to refactor this and write it this way. This is just a value of ratio, and we can take this value and divide it by 3, by 12, or multiply it to end up with different units. And it helps a lot. Notice also that here we are instantiating our class template with strings. Those are also non-type template parameters, just values. And this is really helpful to be able to provide definition for the unit in a physical library in one line, rather than providing several type traits or functions that provide information about the symbol, about the ratio, about some correspondence of types, which is typical to other libraries, and all of them try to wrap it with macro for it to be easy to use. This one doesn't need any macros and doesn't use any macros, and actually no macros are allowed in the standard, so it will not be possible to standardize it if it was using macros. So I had to find better ways to do it. But this is only one of the reasons to use this ratio. Here are some others. For example, before, to compare two ratios, if ratio multiply 2 by 3/8 is the same as ratio 3/4, I had to write something like this. Now my static asserts looks like this one, and they just work. before, to multiply all of the ratios on the exponent lists of some dimensions, I had to write those class templates that was like recursive instantiation until the end case, where multiplying each of the component by another one. With using ratios as values, I can just use fold expressions in one function template, which makes it much simpler to develop, much simpler to reason about, and much faster to compile. With my experience in this library working with non-template parameters, I would say that this feature is one of the most significant C++ improvements in template metaprogramming of the last decade. There are so many new use cases opened thanks to this feature that it's really, I'm really enthusiastic about this feature, and I hope to see it more used in the future. Basically, my recommendation is if a template parameter behaves like a value, not like a type, but like a value, it probably should be a non-template parameter. Try it and maybe provide some feedback how it works for you, because it worked great for me. Next feature I would like to address here are concepts. One of the biggest improvements, one of the bigger changes in C++ 20. The question is, how do you feel about such an interface? We have function foo that takes some parameter t and returns something. This is something we don't like, something that we are having fun of, right? We are laughing that C does these things, we are better, we have strong types in the language. But how it differs from this, or this, or actually in C++ 20 you can rewrite this as this, because we have generic functions, or class template that takes any type. Of course, the difference is that this will fail in runtime, this will fail at compile time. But from the interface point of view, from the documentation point of view, for example, when you want to go to cpreference.com or any other documentation generated by some tool, you don't know anything about this function. You don't know what to provide, what to pass, what's being returned from it, right? I would say that unconstrained template parameters are the void pointer of C++. And we can do better, and we should do better in order to improve our interfaces. So what are concepts? Class, function, variable, alias templates, and non-template functions can be associated with some constraints. Constraints basically specify the requirements on template arguments and can be used to select the most appropriate function overloads and template specializations. And when we name a set of such constraints, we end up with a concept. So concept is a named predicate that works at compile time, and it's a part of the interface of a template. So it's provided in any code-generated documentation from our code, or cpreference.com, or the standard itself. On the IC committee meetings in LEWG, we agreed on some categories of concepts. We agreed that we have predicates, like derived from, capabilities, that basically provide single requirement concepts, like something is swappable, or abstractions, like bidirectional iterator, if the type I behaves here like a bidirectional iterator, right? So it has to be at least 4 iterator, it has to be derived from the bidirectional iterator tag, and we are requiring that the value of the bidirectional iterator has to be decremented both in pre and post decrementation, and provide the reference to or value to the type itself. And these are the 3 categories that we defined so far. Those came out from the ranges library that we first Eric and Casey implemented on GitHub and then standardized for C++20. So this is the world we are seeing right now. Maybe it doesn't look right, maybe it's not familiar, but sometimes we can look from another angle to the same situation. Let's, for example, make this map upside down. And I think it starts to be more familiar to you, right? From my, from my experience, we want to have more categories of concepts. Let's come back to our ratio multiply class template that we have right now in the standard. It just takes two different types. If the name was not expressive enough, I would have a hard time to find out what I can put into this ratio multiply, right? I could try to put string and std_milli to this ratio multiply, because it says it takes everything, right? Type name means this is void star, I take everything. And then I have a huge error log saying that I did something stupid. So I would argue that we need more types of categories. For example, we may have concept any ratio that just conforms to the type trait written is ratio, and type trait is ratio by default is false, and it's true when actually the type T provided is a specialization of ratio. Just this. For the long time, I provided those types with big letter at the front because ratio is already taken, right? So how to name a concept that means instantiation of the type. If you have type ratio, how to name the concept that matches any ratio instantiation. But it seems that maybe prefix any right now is free, because at the very beginning we said that prefix any should be reserved for polymorphic wrappers. But on the last discussions about any invocable and the discussion and actually the outcome to rename it to move only function, maybe any can be used for such concepts. Otherwise, I don't know what's a good name for this category, but I think it's really useful. The authors of the range.sts had the experience that getting concept definitions and algorithm constraints right is hard. And this is true for the case of range.sts. I don't argue with that, but this is often oversimplified, stating that basically defining concepts is hard. So basically we should keep the number of them small, because it's later on it's hard to fix them if you make them wrong. But again, because this was range.sts. We know right now that map and basically the scope here may be bigger, right? For example, if you have this an instantiation of a class template, concept and type trait. This concept is easy to prove correct, right? It's not hard to verify if it's correct or not. It's easy to prove it correct, and it works. If I provide it as a ratio multiply argument here and make something silly, I will had a really nice error log saying that constraints are not satisfied, right? Because the expression is ratio evaluated to false for the type provided. So this is one of the cases. Another one may be ratio-like type. So it's not specialization of ratio class template, but it has numerator and denominator members. And maybe that's enough to specify things for ratio multiply, although I'm not sure about it, but for some cases it may be enough. Again, it's really easy to prove that such concept is correct. So why to limit the number of concepts because of such simple definitions that are really helpful? And again, providing this to this ratio multiply and making some silly instantiation ends up with information that constraints are not satisfied because there is no num and then in basic string. Notice how basic string works and how nasty it looks like, because this is an alias, right? If toString was a strong type rather than an alias, this error would be much easier to reason about. Again, the outcomes from the first chapter and some use cases could be useful here, but we don't have strong types in the language. If we had those, this error would be much easier to think and reason about. Maybe we do not need name concepts. Maybe we don't need to extend the collection of concepts we have in the standard library. Maybe we can just live with constraints in form of type traits. But I would ask, what is the difference in having more concepts or more type traits? Right? If concept is defined by the type trait, then providing the type trait is hard, not the concept itself. So if you provide a type trait already, then concept is for free. And named concepts are really useful. For example, in my library, if I want to implement a function called calculate fine for speeding, I'm returning price here, getting speed. Speed may be a concept that is quantity of dimension speed, where quantity of requires t to be quantity, d to be dimension, and basically dimension to be equivalent to the dimension specified by the quantity provided. And quantity is specialization of quantity, so exactly the type trait we spoke about. Dimension is either base dimension or derived dimension. Derived dimension is again derived from specialization of some class template, and base dimension is derived from another class template. Because I want to have strong types here, that's why these are derived, not just a specialization of, right? Some guys say that concepts are just syntactic sugar to make things easier to type, easier to maintain, so basically you can replace those with old practices. But this is not the true. For example, how would you constrain the function return type with old practices like enable if? How would you constrain a user variable in a stack of the function, taking the value from this function? Yes, you can constrain class templates, but it's not easy, right? You have to provide additional template parameters and provide undefined primary definition, and then provide specializations depending on the class on the parameter of this additional class template parameter here. But with concepts, it's easy. You just provide concepts here, and it works. Another use case is here. What is the difference between those two? We have wrapper of type T and wrapper of type T. Data, data. This one takes a function template foo with parameter u, that's parameter of this template, and this one has the same parameter. And you want to constrain this, that it should work only if the type T for a class template is an integral type, both with enable if and requires clause here. This is innocent looking code that doesn't work. The left column here is broken. This fine, so substitution failure is not an error, will not happen in the left case, because T is not a current template parameter of this function template. It's fixed for entire class. In order to make it work, you have to make a workaround. You have to introduce additional template parameter, make sphin on this additional template parameter, and default it from T. In case of concepts, it just works. Concepts are not sphin, and actually, based on my experience, they are much faster to compile than sphin. Also, if you want to constrain a regular function that's even not a template, with constraints, you can do this easily. Here, you have to make this function bool a class template again. Sorry, a function template again. Right? That will take parameter z, that's default to t, and then make spina on this one. There are a lot of benefits of use if concepts. First of all, they clearly state the design intent for the interface. They are provided in documentation of this interface. So the user knows exactly what's expected to be provided from him or her to be provided as a type to this template. They simplify and extend spina, right? They are much more than just enable if, much better than void t. And introduce some new use cases that are not possible with spina techniques that we had so far. And also greatly improve error messages. Maybe they don't make errors shorter, but at least make them more expressive. The errors happen on the border, on the interface of the function template that you want to call, or a class template to instantiate, and not deeply nested in the stack of the function implementation, saying that something didn't compile. It's just like a guard on the entrance to the door, saying you can either enter or not, and if not, you basically have the full information provided why you are not allowed to enter. And this is really helpful in understanding what's the problem in your implementation. In case you want to learn more about concepts, I think that there may be some still open places for my session on Sunday. So if you like it and you would like to learn about concepts, about my experience with the Unix library that I implemented and how concepts can be applied there, please feel free to register, because there still may be some places left, and you can still probably join us on Sunday. Okay, but the world is even bigger. It is round. It is not flat. There are more things that we can do with templates if we had support in the language. So let's talk about things that we can actually extend in the language to provide better experience, more functionality to our, let's say, metaprogramming. But I don't like this word. I always say that metaprogramming was before concepts in Boost and its similar libraries. Right now we just have templates. As I said before, sometimes I don't want to have named concepts for every type. I don't want to have information like any vector, any string, any ratio for any type in the library. It doesn't have sense, right? It would be enough to have one concept saying satisfies. Let me provide type trait. I create is ratio type trait, and I can say satisfies is ratio for ratio multiply. And again, it is fine, assuming that my type trait is provided as class template. But lately, more and more type traits or traits are implemented as the variable traits, because we found out that it's less to type, faster to compile, but this cannot be provided to satisfies, because this is a variable template, not a class template. There is no syntax in the language that allows me to put a variable template here. Only types can be created from those generators. So there is a proposal, 2008, you can Google for it, that basically tries to extend this to make variable templates a first-class citizen in C++. So you can put trait based on bool, or actually trait that bases on any other type, like ratio or whatever, to such template. Why variable traits are worse than class templates? I don't think so. We maybe just don't have enough use cases for those through the years. especially before non-type parameters were not extended with new possible use cases. But now I think having non-type parameters as templates here may help a lot. This is one case for traits. This is another case. There are already a lot of customization points in the standard library that base on variable traits. For example, in ranges library, we have enabled borrow range, we have disabled size range, we have enabled view. All of those are variable traits. And if you would like to use them as template parameters for another templates, you'd have to pack them in a type, which doesn't have much sense, as we have those in this form already in the standard. Another use case. We have stud numbers in C++20. It turned out that for some units, for example, degree and radian conversion, rational factor is not enough. We need irrational factor too. And now we can provide stud numbers p_v as a variable template to make this definition of scaled unit for degree. Those are only a few use cases of this feature. If you have ideas for more, please let me know, because I was asked by the evolution working group to provide more examples, motivating examples to the paper, but it was basically friendly accepted by the incubator already. So I'm looking for more use cases. If you have some that I didn't cover so far, please let me know. You can be the contributor for the proposal, and then we can push this paper together for C++23. But this is not all. We have different parameter kinds in the language, right? You probably are aware of those. We can have types, non-types, or templates. Right? So we can provide integer, free, or a generator to our template. But all of those are distinct kinds. Imagine that you have a universal template parameter kind that matches any of the ones from the previous slide. Can be replaced with any kind of template parameter, type, non-type, or template. The syntax is still not yet decided. I had a different syntax in mind. Gaspar, that's my co-author from the proposal, had different idea. Actually, this one. And this one is right now the one that we are using in the paper, but we can find out and end up with a different spelling for this. So please don't be basically framed with this spelling. If you have better ideas, actually, you are welcome to provide those for us, so we know what we can also consider here for the bike shedding if it happens in the committee. But consider that this matches any parameter kind. And this matches any pack of any parameter kinds. It opens us the doors for more interesting use cases that are not possible for now. For example, until now, I'm not allowed, it's not possible to create a specialization of concept or type trait. For example, if I want to create an specialization of string, it will work because I can say a list of types, right? If I want to say I would like to verify it, I would like to make it for vector, it will also work. But for example, it will not work for array already, because array has list not only of types as template parameters, but also there's a value, the size of the array at the end. Class templates like ratio take 2 values. So they also cannot meet with this parameter pack right now, if it's fixed for types only. Having the information that I just want to have any type here, and I don't care what are the template parameters and what are the kind of them, allows us to write one generic type trait saying is specialization of, and then possibly a concept named specialization of. That will basically allow us to write all of those class-specific type traits to find if it's an instantiation, a specialization of this type trait in one simple way. But right now it is not possible because we have to say that first is either those are types or values or generators. And you cannot provide one list that matches all. So for example, my ratio multiply could be implemented as a specialization of ratio, specialization of ratio. And it would work just fine. We'll have an error saying that constants are not specified because basic string a long alias here for the instantiation basically does not meet the specialization of the type provided for ratio. Another use case. For example, let's assume that units in my library are created as functions. This is how those functions would be implemented in C, right? We'll have a descriptive name and then void pointers everywhere. In C++, we do better, right? We have strong types. So you can provide strong types here and still provide descriptive names. But we already learned, if all of those provide derived unit, it's better to have a function called derived unit with just a different set of arguments. Because this function creates a derived unit. This is a factorial function for a derived unit. Right? And this is what we used to already. But I'm not working on functions and values. I'm working on types here. So this is what I have right now. I have class templates for every kind of unit with different set of parameters. Before concepts, those were just type names. And possibly some values right now with C++20. But with concepts, I can exactly specify what is the strong type, let's say, for those template parameters, like in the case of overloaded functions in C++. So now, I could specify that derived unit is just a class template that has any set of arguments, and then provide specializations for every type of creation of those. And notice that I have types and I have some values here. That's why it's not possible right now in today's state. Because I cannot specify this as a class template that takes any kind of parameters. So right now, I have specified length like this one, time like this one, spin by this one. With the change proposed, I could just specify those as derived units, the same way as all those overloaded functions provided on the previous slides. Okay, so this is all about the possible future extensions I have for today. And let's scope and move to performance. In order to talk about performance, let's talk about MetaBench. MetaBench is a compile time benchmarking tool started by Louis Dion for his HANA library in 2016. It's just a CMake module that simplifies compile time macro benchmarking. Can be used to benchmark precise parts of C++ file, not entire files, but just precise parts of it. If you want to look more, look into this address, metaben.chi, where you will find more information about this tool. You will also find comparison of several metaprogramming algorithms from different libraries and how they relate to each other in terms of performance. How the tests are implemented? They're implemented in CMake. You provide different data sets for different input files. Those files are Ruby files. And you provide input data, values for the test, the name of it for the data set, and so on. And then you provide a chart. Chart basically has a title, subtitle, and aggregates the data sets. This Ruby file is implemented in this way. You provide some definitions. You provide some things to be tested. And if defined meta branch, this is something that's being tested. Else, you provide a branch that is being used as a reference to find out what's the base of this compilation. So you are looking for a difference, not just how long does it take to compile. And you have Ruby way of generating stuff. Provide a loop, provide the name in the structure so it doesn't collide, we do not break one definition rule, and then we are done. This is what we can type, and this is what gets generated by MetaBench. Actually, both of them are generated by MetaBench. Sorry. This is generated by MetaBench for types, so we are going to compare stud ratio, and also we are going to compare mile ratio, that's NTTP, so non-typeable parameter. Here I'm comparing to creating an alias, so I want to just find the performance cost of creating this type, not of creating an alias inside the structure. So I'm creating the same number of aliases, and here I want to find out what's the difference between creating of instance of my type compared to the Boolean value provided as well in the same structure. And there are many of those, right? Generated by the generator. And here the outcome from the test. Stud ratio, compilation type. Stud ratio using context functions like GCD that I shown you. Please note that none of the standard library implementations known to me do not use it, even though it's totally possible with all of the things that we have already in place. Because it would mean that basically C++ 11 and 14 implementations will be different, maybe not ABI compatible and so on. Although it's compile time, so it wouldn't be an ABI issue. But still, it will require some branch and maybe some introduce some additional maintenance costs for the developers to maintain two different branches of the same let's say algorithm of working on ratios. But still, using the NTTP ratio, it's way faster than any other solution here. This is for multiplication and divisions of ratios. It also includes, of course, creation of the ratio instance. However, I also benchmarked only the creation process. So notice what is the scale here, 40 seconds, 5 seconds, 10 seconds, right? And the creation of it in this process, it's up to 2 seconds. So it's basically really short and small part of it. But notice that the graphs look differently right now. Stud ratio and ratio using context are of similar performance, but NTTP ratio is much slower for creation case. And this is known. Hannah talked about this already in 2019 on C++ Now. She named this the concepts problem. It is really slow. For her use case, some algorithms take 2 minutes on GCC, 40 seconds on Clang, but only 5 seconds on PHP. We can do better for concepts, for sure. If PHP is that faster than any other C++ compiler, we can do better, we can improve concepts, but please note that concepts are not for free. In some cases, in some complex operations, if there are a lot of instantiations of class templates, a lot of allocations done by the compilers, it can be proved to be much faster. But for some cases, it's not the case. We have always to measure. And talking about the things about the cost of specific operations, there is a rule of Chiel. Chiel is an intern that worked for Odin, probably still work together. And he basically made the engineering approach to assess compile time performance. He measured that the fastest thing you can do in compile time is looking up for a memoized type. Next is adding one parameter to an alias call. adding parameter to a type, calling an alias, instantiating a class, instantiating a function template, and doing sphinne. It is the slowest thing that you can do. So see how it proves in action. This is a typical implementation of conditional in the standard library. This is how we do it in probably every implementation we have right now. Conditional provides Boolean argument here and case for true and false. By default, points to true. If it's false, then it points to false. And we have a helper for it, an alias, right? With the information gathered by Chiel, we can re-implement this in this way, saying that conditional is a class template, but only of type bool here. And it always points to false. And we have one instantiation, specialization of it for true that returns true. And then this alias conditional t works a bit differently. It instantiates either this one or this one based on the Boolean expression, and then creates an alias template inside this structure. So we are right now trading the number of class template instantiations to the number of aliases instantiations. And we know already that alias is here, class template is here. And we are saving performance. Here are the results. This is typical implementation of stud conditional. This is basically the same one, but without using an alias. And this is one provided with the knowledge we have from Chiel. This is on GCC 10, and this is on Clang 10. As you can see, it is really similar. One of the templates is missing in the Rule of Chiel. There are no variable templates there, right? But probably at this point where he was doing the measurements, variable templates were quite new to the language. So let's measure them by ourselves. For example, traditionally, isSame is implemented this way. By default, it points to false type. If it's exactly the same type, it's true type. And we have a helper for it, right? That takes _v and provides the value from the type trait. We can implement this easily with variable templates that I mentioned before. And if we really need it, we can provide the isSame as a bool constant for the users that require class template rather than the variable traits. And what's the performance outcome from it? On GCC 10, this is usage of stud isSame v. We are paying for variable template instantiation here, and pure isSame : value is the blue one, right? So it's faster than using the helper. However, the red one is just using a variable template provided on the previous slide. So if you implement this just with a variable template, it's way faster than anything else. And then if you really require class template, you can go for the green one. So this is this additional class template provided for the variable template implementation. But in most cases, you are interested in this, not in this. So this should be faster, this may be slower. For Clang, it is similar. Actually, I spoke about this for the first time on CPPCon, I think like 2019. And later on, because I didn't attend the session, I found out in the recording that another speaker at the same conference was also providing an alternative implementation for isSame. What a coincidence, right? Two speakers at the same conference talking how to improve isSame. And this was the proposed implementation. The other speaker proposed moving out the false case to non-templated structure, so it's common to all of the instantiations. And then provide the instantiation only for the true case, and depend on the overload resolution to find out the result. It looks nice, reasonable, but I measured. This is this line on Clang. It works. It's not much slower than anything else, but it is significantly slower. You can measure the difference. But this is on Clang. And then I measured on GCC and I thought that the compiler hanged. This is what happened on GCC with this implementation. Notice that all other results are here at the very bottom. Always we have to measure what we are trying to get in if you are striving for performance. Okay, so we're talking a lot about concepts. So what is the performance of concepts? I don't have much measurement on the production code base yet, but I expect to have it at some point. But I checked a simple example like this one. I'm calling either one function foo or another function foo depending on if it's even or odd. And I'm either using Sphinx or I'm using constraints here to make the same work. Also, I'm checking with concept if concept to do the same and verify what is the performance of those. On GC10, Sphinx is this one. If concept and concept are here. Notice that concept and if concept have exactly or really similar performance characteristics, way better than Sphinx. On Clang, similar results. From my experience, you can also improve a bit performance if you skip concepts usage in some cases. Concepts are needed for public interfaces for the user, right? So the user can provide correct types. Like for example, if you have specified dimension, it has a list of exponents, I want to check if actually types provided here are exponents. Also, if I want to create dimension divide helper, I want to make sure that those types provided here are dimensions. But then when I'm going to dimension divide detail implementation, I may actually skip those already here and here because they were validated here. Users should not call those functions. I already validated that those are okay. I may try to skip those, even though they should be memorized by the compiler. It may save some CPU cycles during compile time. Also, as I already verified that dimension is all properly curated with exponents, when I provide this here as a specialization for exponents of dimension, I don't have to type that those are exponents because there is no possibility to create a dimension without those types not being exponents, thanks to this definition. So I don't have to retype it here only for specialization, type specialization case. Right? So I'm here putting those type names rather than concepts, and this saves some CPU cycles. Not many, but some. Here are some tests I did for making dimension for 200 times. And there is blue line for no concepts, green line for concepts everywhere, and orange one that basically follows the rules provided on the previous slide. You can find out that basically concepts are not that expensive. Of course, there is some cost because there is something you are using, right? We are agreeing to paying what we are using. Concepts give a lot of benefits. It's not just that we are paying for something we don't use. So there is some additional benefit of using concepts, and the performance hit is not that huge, as you can see. So I can only recommend you once again going and using concepts. If you want to learn more about compile time programming, about compile time performance of different algorithms, I recommend you once again going to this MetaBench site and compare how, for example, different libraries compare in sort or any other algorithm. And then looking into those libraries to find out how actually the authors implemented this, so it is the fastest implementation in the world. Takeaways. Think about end-user experience, not only about your convenience as a developer. Right? Provide strong types wherever possible for your template instantiations. As I already said, if string was a strong type rather than an alias, many of compiler errors would be much easier to reason about and much shorter. Use C++ concepts to express compile time contracts, to improve productivity, to improve compile time errors. Use non-type template parameters when a template parameter represents a value rather than a type. It will provide many benefits in the interface, like for example, you'll be able to use fault expressions, and also should be faster to compile in many cases. Optimize compile time performance. Run tools like MetaBench. Maybe metaprogramming is free at runtime, so we are doing this to save in runtime, but we still have to compile this code, right? If there are many ways to do the same, it's useful to find out which one is the fastest to compile. And always measure. Because sometimes claiming that it has to be faster because I think so based on my experience, even if you are a speaker on CPCon, it may not be true. I'm wrong all of the time. I always measure too. And thank you. And let's look into the questions. And the most rated question in Q&A is what parts of concepts cannot be simulated with C++17? This is something that I think I covered already. I mentioned that, for example, it's not that easy or maybe even not possible to constrain a function return type with C++17 Spine. You can just say auto and that's all you can do if you don't know exactly what you're going to return. But with concepts, you can say, for example, speed auto, and then you will make sure that this is some quantity of some system with some units, but still that complies to speed dimension, for example. So you can constrain those and provide more information. Another point that is not possible with C++17, you cannot constrain a variable on a stack of the function. Saying, if you just call make foo, you can assign this make foo to auto only. And you cannot say, well, I wanted speed from this foo. Right? You cannot constrain this just to make sure that foo returns the thing that you already that you expected. And to provide more information to the user, because having auto only in the code sometimes it's too verbose and basically it doesn't provide any information about the type. That's why many people hate auto, right? But sometimes you cannot express the type explicitly because no specific type is returned. It may return different types. And then you have to use auto only. But with concepts, you can constrain saying that only some kinds of types are possible. I will not take double or string here. And probably there could be some other cases, but those are probably the most important ones. So this is answered live. Another question. Do you think a stronger version of concepts like Rust rates, where all functionality must be explicitly required by concepts, will come to C++ in the future? Or are concepts the best we can get? Actually, I'm not familiar with Rust rates, so it's hard for me to answer this. From my experience, concepts work fine as they are right now, and I don't see much issues with those. Maybe I should look more into Rust, but for now I'm not able to answer and compare it to Rust rates because I don't know much about it. And I think those are the most rated questions, and we are out of time right now. If you have any more questions, we can meet by the table on the conference. So thank you very much for joining this talk. I hope that you enjoyed it, and basically maybe it will help you provide better metaprogramming code in your using better usage of templates in your projects. So thank you very much. Take care. and see you soon.